Okay, well, I guess I'll get started. This is Bob Capetta, and this lesson is on Riemann sums. So we're going to use this approach to determine what the area under the curve is going to be as a precursor for our more advanced strategies for evaluating integrals. There's a couple facts that we need to start with that you absolutely have to have. First off, the sum as I goes from 1 to n of I is a half n squared plus a half n. So keep that handy. What do I mean by that? So for example, if I said the sum as I goes from 1 to 5 of I, that's 1 plus 2 plus 3 plus 4 plus 5, 9, 12, 13, 14, 15. How about if n equals 5, what is a half n squared plus a half n? That would give me a half times 5 squared plus a half times 5. So 25 halves plus 5 halves is 30 halves, or 15, which makes me happy. So again, here's the fact that we need. The sum as I goes from 1 to n of I is a half n squared plus a half n. Hello, Isaiah and Greg. I'm glad you made it. Hopefully we'll get a few more people here. If not, they can watch it later. We also need to look at the sum as I goes from 1 to n of I squared. Now, the version of this I prefer is not the same one that shows up in textbooks, but I like this one. It's 1/3 n cubed plus 1/2 n squared plus 1/6 n. So let's take a look at the sum as I goes from 1 to 4 of I squared. That's 1 squared plus 2 squared plus 3 squared plus 4 squared. 69 is 25, 4 is 29, and 1 is 30. And now if we plug the 4 in up there, so if we have n equals 4, we'd have a third n cubed, a third times 4 cubed, there to help us do that computation. 1/3 times 4 to the third power plus 1/2 times 4 to the second power. We need the sum is I goes from 1 to n of I is a half n squared plus a half n. The sum as I goes from 1 to n of I squared is a third n cubed plus a half n squared plus a 6th n. We want to make sure we keep those in mind. All right, let's start with a relatively straightforward problem, and then we'll see if we can extend to more challenging ones. So how about the integral from 0 to 3 of 2x plus 1 dx? Now, so this is 0, this is 3. That height, of course, is 1. So this area here, this is 3 is the width, 1 is the height. And this area is 3. From 1 to 7, the area of this triangle is 1/2 base times height. The area of the triangle is 9. So this is, if that's 9 and that's 3, obviously not drawn to scale. This thing should be 12. So I'm going to exaggerate this a little bit. And we're going to see what this is going to look like. So I can approximate this with 4 rectangles, with 8 rectangles, with 12 rectangles. Let's try 4 rectangles first to approximate this area. We're going to use 4 rectangles. I'm going to draw 4 rectangles to approximate what the area under the curve is. Now notice these rectangles are all bigger if I use right endpoints. They would be smaller if I would use left endpoints. I'm going to call this rectangle 1, rectangle 2, rectangle 3, rectangle 4. And I want to see what that area is going to be. It's going to be more than 12. Hopefully not a whole lot more than 12, but a little more than 12. So how am I going to describe this? Rectangle 1, rectangle 2, rectangle 3, rectangle 4. You'll notice the width on these rectangles is all the same. I have 0 to 3 divided into 4 pieces. So the width is 3 minus 0 over 4, or 3/4. Each one of these things is 3/4 wide. So this guy is 3/4. That's 6/4, also known as 3/2. This is 9/4, and that's 12/4, also known as 3. So the width of every one of those rectangles is 3/4. Width is 3/4. Width is 3/4. Width is 3/4. Width is 3/4. Now what's the height? The next height is the value of the function at 3/2. Next one is the value of the function at 9/4. And the last one is the value of the function at 3. But what is our function? Our function is 2x plus 1. So we're going to use that 2x plus 1. We're going to plug all those values in and see what we get. If I plug in 3/4, 2x plus 1 gives me 2.5. If I plug in 3/2, I get 4. 2 times 3/2. And if I plug in 3, 2 times 3 is 6, plus 1 is 7. So that's the height of each one of those rectangles. But what do I need? I need the area. I'm trying to find the area under the curve. How am I going to find the area under the curve? I'm approximating it with these 4 rectangles. But area is width times height. So I have 3/4 times 2.5. 3/4 times 2.5 gives me 1.875. 3/4 times 4, of course, gives me 3. 3/4 times 5.5 gives me 4.125. And 3/4 times 7 gives me 5.25. So the area of the 4 rectangles is an approximation for the area under the curve. Notice, under the green is a little bit more. So the area of the rectangles, if I add all those up, 1.875 plus 3 plus 4.125 plus 5.25 gives me 14.25. Which is more than 12, as I expected. You know, quite a bit of error, but again, looking at that, even from my crudely drawn picture, you can see it's going to be off by quite a bit. So I could get a better approximation if I used 8 rectangles or 8,000 rectangles. But we're going to take the limit as n goes to infinity of having n rectangles. That's going to be our approach. We're going to evaluate this thing as a limit of a Riemann sum. So here we go. Let's look at it again, and let's construct a large number of rectangles to discuss this. 0 to 3 of 2x plus 1 dx. From geometry, we think it's going to be 12. We need to figure out some way to describe this. So here's our picture again. Here's 3. I'm going to draw in n rectangles. Here's my first rectangle. There's my second rectangle. Here's my third rectangle. Here's my fourth rectangle. Dot, dot, dot. Here's my nth rectangle. So this is rectangle 1, rectangle 2, rectangle 3, rectangle 4, rectangle n. And we're going to think of n going to infinity. We're going to think of the number of rectangles that we're going to use going to infinity. Now this starts at 0 and ends at 3. I am breaking 0 to 3 up into n equal pieces. So what is the width of each piece? The width of each piece is 3 minus 0 divided by n. 3 minus 0, the total width, divided by n equal rectangles. The width of each rectangle is 3 over n. So this guy is 3 over n. This next guy is 3 over n times 2. The next guy is 3 over n times 3. The next guy is 3 over n times 4. And the last guy here is 3 over n times n, which of course is the same as 3. So 3 over n times 1, 3 over n times 2, 3 over n times 3, 3 over n. So again, integral from 0 to 3, 2x plus 1 dx. Let's make a very good picture. Okay, here is our first rectangle. Here's our second rectangle. Our third rectangle, again, let's draw the green top to be consistent with what I did before. Third rectangle, the green top supposed to be. Fourth rectangle, and nth rectangle. It's very important to visualize this and see how all these pieces are going to fit together. And then the last one is the nth rectangle. So n rectangles, 0 to 3, the width is 3 over n. So again, this piece is 3 over n times 1. This guy, that number is 3 over n times 2. This one is 3 over n times 3. This one is 3 over n times 4. And this last piece is 3 over n times n. Okay. We're going to add up all of those rectangles. So we have rectangle 1, rectangle 2, rectangle 3. The width of all of them is 3 over n. What is the height of rectangle 1? It's the height of rectangle 1 is f, the value of the function, which is 2x plus 1, of 3 over n times 1. At 3 over n times 2, we're using right endpoints. F of 3 over n times 2. Of rectangle 3, the height is f of 3 over n times 3. So these are all of the pieces that we need to look at. We need to build our total area by multiplying the width times the height and then going from there. So let's see if we can do that. So again, we have integral from 0 to 3, 3, rectangle 4, dot, 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 rectangle n. We're going to figure out the area of each of those n rectangles. First, I need the width. So we were going from 0 to 3, broken up into n pieces. The width of each piece is 3 over n. Clarify that. F of x is 2x plus 1. So f of 3 over n times 1. The rectangle 2. Here's rectangle 2. There's its height. Is the value of the function at 3 over n times 2. Rectangle 3, its height is here. That's the value of the function at 3 over n times 3. Rectangle 4, f of 3 over n times 4. Rectangle n, f of 3 over n times n, which of course is the same as f of 3. Right endpoints. And again, I know what f of x is. F of x is 2x plus 1. So what is the area? Area is width times height. So 3 over n of 3 over n times 2. Then we get 3 over n times f of 3 over n times 3. 3 over n times f of 3 over n times 4. Finally, 3 over n times f of 3 over n times n. I want to add all of those together. Do we see that? If I add all those together, all of these guys have a 3 over n in them. So the total area is adding them all up. 3 over n times f of 3 over n times 1 plus 3 over n times f of 3 over n times 2 plus 3 over n times f of 3 over n times 3 plus dot, 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 it ends with plus 3 over n times f of 3 over n times n. Now, is there a way for me to simplify that? How can I simplify this? Whoops, problems. 3 over n. I get f of 3 over n times 1 plus f of 3 over n times 2 plus f of 3 over n times 3 plus dot, 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 plus f of 3 over n times n. So what's changing here? Hello, Eileen. Equals the sum as I goes from 1 to n. And where I have this changing, 1, 2, 3, dot, 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 to n, make that an I. So I get 3 over n times f of 3 over n times I. And that's my total area. And the actual area, that's the area for what? For n rectangles. This is the total area for n rectangles. But what I want is I want my integral. So my integral 0 to 3 of 2x plus 1 dx is going to be what? It's going to be the limit as n goes to infinity of the area of n rectangles, which is this. Sum is I goes from 1 to n of 3 over n times f of 3 over n times I. Okie doke. What was f? F of x was 2x plus 1. So this equals limit as n goes to infinity of 3 over n times f of 3i over n, which equals, make a little note off to the side, f of x is 2x plus 1. So f of 3i over n is 2 times 3i over n plus 1, which is 6i over 8 of 3 over n times 6i over n plus 1. As n goes to infinity, 18i over n squared plus 3 over n. And I lost a sum. I need a sum in all this. Sum, 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 as I goes from 1 to n, so you know that's what that means. So let me write it one more time just to clarify it. The limit as n goes to infinity of the sum as I goes from 1 to n of 18i over n squared plus 3 over n. So we have this. Now we've got to take the sum of this piece plus the sum of that piece. What is that going to look like? This equals the limit as n goes to infinity of the sum as I goes from 1 to n of 18i over n squared plus the sum as I goes from 1 to n of 3 over n. So now I need a little bit of algebra work here to recognize that we can pull constants out in front. So I'll pull the 18 over n squared out in front of the sigma sign. So I get the limit as n goes to infinity, 18 over n squared times the sum as I goes from 1 to n of I, 3 over n plus dot, dot, dot plus 3 over n. It means 3 over n times. 3 over n times, which the answer is just 3. So this piece, the sum as I goes from 1 to n of 3 over n times just becomes 3. Now you'll recall that I gave you the formula for the sum as I goes from 1 to n of I. It was a half n squared plus a half n. So I will say this is the limit as n goes to infinity of 18 over n squared times sum as I goes from 1 to n of I, a half n squared plus a half n, plus this 3. And then we'll see where we are now. So what do we have? Limit as n goes to infinity, 18 over 2, 9 n squared, that goes away. 18 over 2 is 9 n over n squared. As n goes to infinity, what happens to this? 9 over a very large number goes to 0. So this is 9 plus 0 plus 3, which equals 12, which makes me very happy. That's exactly what I thought it would be when I did it, because we did it with geometry, and that was the answer that we had. So that is one question that we have here, working with the limits of a Riemann sum. And I think maybe I'll end the video here. I will upload another video at some point in the next few days that will look at how we do one of these for a quadratic, or one that has an x squared. But that's a pretty good start. So I will let you go with that, and I will send you a homework set, and keep working hard. Thanks, my friends.